Okay, one thing we
Maybe
can see, yeah.
it would like converge more towards 0.
Yeah, it seems to be kind of a conversion, right? So if you track the solution where it is equal to 1, the solution where it is the part of x where the solution is equal to 1 has moved towards the middle. So the solution would be equal to 1 here as opposed to here, right? So if we link them, the contour would look like this. This is where the solution is going to be highest. And similarly, -1 has also converged towards the middle. So the contour where the solution is the lowest, the valley, would follow a line that moves towards the left. And the solution where it is 0 seems to be unchanged, right? So the middle of the contour line would stay vertical. And now, if you look at all other parts of the solution, it basically looks like that the part of the solution where it is moving towards the right, that coincides with the part of the solution where u is positive, has contours that are sloping towards the right. And also, the part of the contour where the solution u is negative now slopes towards the left, right? And the higher the value of u is, the more towards the right the contour would slope, and the lower, the more negative the solution is, the more the contour would slope towards the right. Not coincidentally, this is pretty much the same as our green case where our a is a constant, right? So if a is a constant and positive, all the contours would slope towards the right. And if a is negative, for example, if a is negative, then if we draw a corresponding contour, if we draw a contour like that, the contours would slope towards the left, right? Because the solution, as time advances, would move towards the left. All right. So it seems that when we have a nonlinear differential equation, and we want to analyze analytically how the solution would behave so that we can check against our numerical solution, it seems that the correct behavior we would expect is that we should follow the contour lines of the solution, the x in the space and time diagram. And the contour, the slope of the contour is intimately related to the coefficient or whatever function or number is before the du dx. All right. Okay, so now you can see several things, right? So one is that if these lines, the lines on the contour is going to be something we call characteristics, right? The lines are going to be called the characteristic lines. One thing we can see is that these lines would follow a slope that actually depends on the solution u. And if the slope of the line depends on the solution, and the solution, remember this is a contour line, right? So along the contour, the solution value doesn't change. I mean, that's the definition of a contour. It is the line on which the value of the solution doesn't change. It's the same. So then the slope would actually be a constant because the slope depends on solution and the solution doesn't change on the contour. So the slope doesn't change as you move along the contour, which means the contour lines are actually straight lines. All right, we can see it from MATLAB in our case. In our case, we have t that signifies time, we have x that signifies the space, and we have a solution u. So if we actually make a figure and do the contour of x, t, and the u, I'm not sure if I need to transpose it or not. Let's try. That works. Nope, that didn't work. So initially I shouldn't get something like this. So let's, oh, that's why. Okay, so I think I I think I'm just drawing the contour of our last segment of integration, right? So you can see that I'm actually using OD45, which returns me the t and u for every segment of 0.01 seconds. So in order for us to get the contour of the whole thing, I think we have to get rid of this this loop and integrate all at once. So let's actually, instead of doing this fancy animation, let's just take t and u equal to time integrating the burgers, right, for the entire 0.15 seconds. So let's run the section for the initial condition and run the section for solving the whole time, and make a figure to show the contour. Right, so this is our contour line, right? So that's basically what we see before. And I think a little bit more dramatic is if we can do a contour F that shows the color and give a little bit more colors. So this would be how the contour looks like. And everybody see that?
So are the yellow parts the peaks?
Yes, let's do a color bar, right? So that'll give you the corresponding color for each, that'll show you what color represent which value. So you see that the yellow parts are corresponding to the highest value of U, and the blue parts corresponds to the lowest value of U. And at t equal to 0, which is the bottom part of the contour line, we see the peaks are exactly at 0.25, and the valley is exactly at 0.75, right? And the positive part slopes towards the right, and the negative part slopes towards the left. And now if you look at this diagram, you can easily extrapolate by your eye and immediately see that the positive part is going to collide with the negative part. Whenever two characteristic lines collapse into each other, a shockwave is formed, right? So this is how shockwaves form. It basically, if different characteristic lines can have different slopes, which is basically almost always the case when you have a nonlinear differential equation like what we are talking about, right? So whenever the coefficient before the du dx is not a constant, it depends on u, then we would have characteristic lines with different slope. And whenever the lines collide with each other, we have a shockwave formed, right? So basically, this tells us that shockwaves are actually not the exception for nonlinear differential equations with a first order time derivative and the first order spatial derivative. It's actually the norm. The only situations where you don't get shockwaves is when the du dx is preceded by a constant. All right, does that make sense?